this page we can see Kevlar. So like what I told you before, Kevlar is the polymer which is used to do the fire resistant structures, for reinforcement in car tires, for aircraft wings, for bulletproof vests. So it seems like they are quite strong. Okay, so let's see how it is formed. So the monomer here, we have benzene 1,4-diamine. So we have a benzene ring, position 1, let's say here, NH2 is there. Position 4, let's say here, NH2 is there. So that's why diamine. Okay, so another monomer, benzene 1,4-diol acid. So benzene is here. So the first carbon, we have the COCl. Okay, so this is the acyl chloride. Yeah? So the other side, COCl again. COCl. Okay, so acyl chloride. So when they want to form polymer, so what happens is the Cl will join up with the H to form HCl. Then the NH will join with the CO to form this structure. NHCO form this structure. Huh? Okay, so then this is the polymer, which is known as Kevlar. Extremely strong. So why extremely strong? Huh? So you can see the reason is here. Delocalizations of pi electrons. Pi electron is available in the benzene ring. Beyond benzene ring on the amide link. So they can move in benzene ring and they can delocalize to the amide bond and then delocalize here and keep continue not just keep moving everywhere in other words. Enhance intermolecular bonding between polymer chains. Because of the delocalization of pi electron, it becomes so strong. So that's how you see the small little electron can make the polymer so strong. So because the electron can move everywhere and make the intermolecular bonding stronger. Flexible, strong, fire resistant, and low density. So you see, that's why we can use it to do the bulletproof vest, because it's flexible. So we can use it to do that kind of clothing. So and it is strong to protect the polish from bullet. And then next point, hydrogen bonding between chains. Okay, so let's see where. So this is the Kevlar polymer, as you can see. Kevlar polymer, hydrogen bond is here. Between the NH, the H form hydrogen bond with the O of another polymer. So likewise here, the O and H. Here also, the O and H. So they can form hydrogen bonds. Okay. Now, Kevlar settled already. So far we have done condensation polymerization, where we have polyester and polyamide. Okay, so now proteins. So proteins, first point, proteins are natural polyamide. Okay, so that means you should expect CONH in the structures. Many polypeptide chains held together by intermolecular forces. Okay, so that means, what is polypeptide? Polypeptide is basically the polymer. So one polymer is held together by another polymer through intermolecular forces. Okay, they can form hydrogen bond, they can form induced dipole, temporary dipole, and so on. Ionic bond also possible actually. So now we see here, amino acids residue. an amino acid unit within a polypeptide chain. Okay, so that means what? Let's see what is amino acid first. Amino acid is something like this. For example, this is amino acid. So where it has the N3H plus and COO minus. So this is the bitter ion form. And another example like valine. Valine is where it has one NH3 plus and one COO minus, and then here it looks different. Okay, so imagine that join out. How they join out? Let's say I draw out at the side here. Okay, so the amino acid, basically the structure is like this. One side is NH2. Let's say I draw the form before they form bitter ion. Then here's something else. Okay, react with another amino acid with NH2 on this side, COOH at the other side. Okay, so they are going through condensation polymerization. They have to remove OH and one of the H here to form H2O. So then they join up to have the CO and H structure. CO and so on. This side NH and so on. Okay, so this whole molecule is called amino acid. Amino acid. Okay. Likewise, this is also amino acid. Amino acid molecule. Okay. So after they form the polymerization, let's say they form the polymer. Okay. So the amino acid residue, as in the note here, amino acid residue is what left over. So which means what? Which means this part. This is the amino acid residue, which has react and condensation happens where this side they lose the OH and this side they lose the H. So what remains is this structure, and this structure is amino acid residue. Okay, so this is also another amino acid residue. Okay, so that's why this point should make sense now, where they said amino acid residue, which is this part or this part, which is the structure in the polymer. Okay, an amino acid unit is an amino acid unit. Original structure is a complete structures of amino acid, but now removing certain parts and we call it amino acid residue. It is a amino acid unit within a polypeptide chain. Polypeptide chain means the polymer. Okay, now let's come back to this table again. So amino acid itself, as you know, the basic structures is like this. So this is before they form bitter ions. So you can see they form bitter ions, where the NH2 becomes NH3 positive, the COOH becomes COO minus. So they have positive charge and negative charge. So in this case, this is non-polar. Non-polar means no charge. No charge. So no delta plus and no delta minus, in other words. No delta plus and delta minus. Okay. You can see here, these structures. Just ignore the NH3 plus and COO minus. Okay, so as they cancel off, they cancel off. The positive charge and the negative charge cancel off. Likewise, here the positive charge and the negative charge cancel off. The remaining structures, you try to imagine the remaining structures is non-polar. It's non-polar. So the remaining structures here is non-polar. Yeah, just the what we call the sp3 hybridization happened to them. Something like alkane. Alkane is non-polar. So the structure that I circle in green is a same or similar structure like alkane, which is non-polar. So that's why this is non-polar. Okay. So then what is polar? Polar. So polar. They said non-polar R group. So if they say non-polar R group, maybe we should take it like this. Non-polar R group. R group refer to this one actually. So should be this one. They have basic structures like NH3 plus, COO minus, and CH. So the non-polar, the R group is this one. So the R group here is non-polar because it is having the structures of alkane. Now polar R group, let's say we look at the R group here. This is the one, the R group. So the R group here is polar because of the OH. So which creates delta positive and delta minus. Oxygen is there. Oxygen is delta negative. So hydrogen becomes delta positive. So likewise, this R group in cysteine, the sulfur and hydrogen. So the sulfur is delta negative. The hydrogen becomes delta positive. So it becomes polar. Okay, polar because of the electronegative atom is there. Now, next one, electrically charged R group. So you see the R group here? It is electrically charged. That means there is a COO minus there. So this is negatively charged. Now you see the R group here? The R group is positively charged for this case. Okay. The basic structures have the charge also, but they cancel off, they cancel off the charge. Positive and negative cancel off. So the net charge is because of this. COO negative, make it having negative charge. This one have positive charge. Okay, now let's move on. Primary structures, sequence of amino acids in the polypeptide chain. So what is that? That means, let's say you have, first you have to know these are the name of the amino acid. So these are the name. So there are quite many amino acid. So they join up in different order. So for example, let's say this is alanine, then followed by valine, and then followed by serine, cysteine, and so on. Okay, so how they join up, of course, it's determined by genetic, and they join up to form polymer, and that polymer is something like this. You have one amino acid residue join up with another amino acid residue, and so on. They join up. Okay, so when they join up like that, so we call that primary structures. The amino acid join up to form a polymer. So that structure is called primary structures. You can see the sequence of amino acid. That means you can see what amino acid residue is here, 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 here. You can see which one they line up. They line up to form the polymer. So has an amino N-terminal. N-terminal, yeah. So N-terminal means at the end you can see nitrogen. NH3 positive is there. So N-terminal. And carboxylic C-terminal. Carboxylic C terminal is here. You can see at the end of the chain, COO minus is there. This is the C terminal. Polypeptide chains synthesized from N terminal. Hence, amino acid numbered from N terminal to C terminal. Okay, so it means what? I write at the side here. Maybe you are wondering. Synthesized from N terminal. That means what happened? Okay, so I put the explanation here. The reason is the translation direction. Translation direction is what? Is actually the process of making the polypeptide chain. The process of making the polymer. Okay, the process of making the polymer to the text direction. Because when a protein is translated from messenger RNA, it is created from N terminus to C terminus. Amino acid are added to the carboxyl end. Okay, so it means that when you want to make proteins, so the process of making protein start from the N terminus. Start from here. Start from the N terminus and keep making the protein until the C terminus, and then finish. Okay, so in details, that is biology, so no need to care too much. So just remember it. They start from N and finish at C. Now, next one, primary structure stabilized by covalent bond. So you can see the covalent bond everywhere. Covalent bond. The covalent bond is also the peptide bond. Peptide bond. CONH. It's called the peptide bond. But after all, peptide bond is what bond? It's just covalent bond. So it's covalent bond. So that's why covalent bond, peptide bond is just the same. Now, of course, peptide bond is specifically used in protein, so that's why they use peptide bond here. And bonds within amino acid residues. So this is a residue, this is a residue, the bond in between is the peptide bond. This peptide bond is strong, and because of that, it makes the polymer more stable, doesn't break easily. Peptide linkages between residues. So, okay, what is the difference between the first one and the second one? Bond within amino acid residues is all this. Within the amino acid residue, this one. What bond is this? Covalent bond. All these are covalent bond. Okay, covalent bond. And then peptide linkages between residue is this one. This is between one residue and another residue. This is the peptide linkages. So let's move on.